My name's Matthew. Those of you who saw me last year may remember me from such exciting adventures as examining the applications that people use to rent e-scooters, finding out what I could about the front-end APIs that those applications use, and then figure out what information those services were willing to hand over to me as a result. And by doing this, we're able to demonstrate that, oh, well, we could watch people as they ride scooters in almost real time. We could figure out where they lived. We could figure out every scooter that existed in the world belonging to each company and identify markets that they were about to launch in but hadn't publicly announced yet. To be honest, massive surveillance, privacy invasion, nothing very exciting, and there were no crimes. Now, those of you who follow me on Twitter will note that I earlier said that this presentation would also involve no crimes. I'm pleased to announce that that was a lie, and this presentation will contain discussion of actual crimes. So just want to be upfront, you probably shouldn't just do what I do unless you are reasonably confident that the company in question that you do this to will not call the police on you. So honestly, I just sort of assume that it'll be fine, and so far I've been right. So if I'm not here next year because I've been arrested, you'll know that I'm a terrible role model. Also, I don't have much time, a reasonable amount of content. I'm going to be going through stuff very quickly, so you'll probably end up with the impression that I have some idea what I'm doing. I really want to emphasize that every point here where it sounds like I was clever came as a result of me spending an extremely long time doing extremely stupid things and getting nowhere, and then finally getting lucky. So I'm not actually good at this, I'm just really bad at giving up. We're going to be talking about scooters again. These scooters don't speak to the same APIs that the apps do. The scooters have their own backend API. They talk to the internet in order to access it for the most part. They run software. They often have a large local attack surface because for some reason they often expose Bluetooth, which, as we know, is secure. The scooter company we're going to be talking about today is Bird. Bird has a range of scooters. We're going to be talking about stuff that's applicable to all of them. So these are the Bird Slender Boys. These are the Bird Disco Boys, Bird Thick Boys, sort of Space Boys. These are the Bird Zero. We're not going to be talking about those because those use a completely different platform that is also shared with some other scooter companies. So what are we talking about? In the past, these scooters were often just commodity scooters with bits of the electronics replaced, but these days, most of the larger scooter companies are actually using their own customized platforms so that they don't, for instance, just fall apart while someone's riding them, resulting in people being dead. So, however, they have, in many cases, kept elements of the technology the same. And so the first couple of scooters I showed you there were Xiaomi M365s and then Segway ES2s. But even with the modern custom ones, they're still using this same box. Now, this box is very straightforward. It's plastic, it's black, it sits on top of the scooter, and it's got a QR code on it. You scan the QR codes with the app reads out a unique identification number from the QR code, and then it goes and reports that to the API, and then you pay money, and then the scooter goes beep, and then you ride the scooter. Everything's fine. Now, I did not take this picture. I found this picture on the FCC's website. As discussed yesterday, you can find a lot of things by just going to fccid.io, typing in a company name, and then ending up with pictures of the hardware they produce, such as this picture that I cut and paste as the PDF. So this is the top side of the board. It's got various little electronic-y things that I don't really understand because I'm not a hardware person. This one, however, is a Nordic nRF52 Bluetooth controller. This is an STMicro STM32 system on chip. This is a giant modem. The modem, weirdly, has an application processor that's capable of running significantly more software than the rest of the chips on this board put together, and in this case, it's almost entirely unused. So, this side of the board, well, OK, we have some chips. Obviously, we would like to do things with the chips, but how do we do things with the chips? I didn't really want to resort to having to decap chips. Let's not go there. This side of the board, thankfully, helps us out. So over here, you see a bunch of pads that are basically underneath where the Nordic NRF52 was. Here's a very similar looking set of pads that is underneath where the STM32 is. So that implies, well, OK, there's some sort of causal linkage here. What could this be? And the answer is that if you have a cable that looks like this, you have made some poor life choices, because this is a cable that is made out of some patch cables with the plastic filed off and then held together with electrical tape. So if you're doing this professionally, just do a better job than me. I lost so much time to this just not making contact with things. But you end up discovering that these pads are exposing the serial wire debug interface, which is basically just JTAG, but with fewer pins, because JTAG has far too many pins. There's an application called OpenOCD, which speaks various embedded debug protocols, including JTAG and SWD. And there's hardware just called an ST-Link. You can buy cheap ones for almost no money off Amazon. And you plug a bunch of wires into them, plug them into USB, and then you can speak OCD. Sorry, you can speak SWD. So one of the fun things that SWD lets you do is read out the firmware from the running chip, unless various protections have been enabled. So thankfully, these protections were not enabled, and therefore it was straightforward to dump the firmware for both the Nordic chip and the STM32. But as well, you're also able to dump memory states. You're able to even use a GDB stub, connect GDB, set breakpoints, and have the actual physical hardware stop execution whenever you reach a specific address or whenever a specific memory address is written to. So this means that we're basically able to real-time debug and analyze the behavior of the firmware. So later on, that's going to be a lot more useful. But we dump the firmware. The first thing we do is run strings on it. Strings is just a small application that looks for strings of ASCII characters inside a binary. And among the strings was set mode to free drive mode, which sounded very exciting. I like free things. So through this firmware into Ghidra. Ghidra is released by the NSA. It's a reverse engineering toolkit. It's a disassembler, but also a decompiler. It's very good at turning stuff into something that looks kind of like C if you squint hard enough. And it knows ARM, because of course it does. So you put the firmware in there. You tell Ghidra what the memory map of the CPU looks like. You press go, and then suddenly you've got something that approximates source code, which makes it very straightforward to figure out what's going on. So you search for the string set mode to free drive mode. You find that there's one code path that references it, and you find that it's embedded in the middle of a large switch statement. The switch statement takes various commands and does various things in response. So that's good. There appears to be a command we can send to it that enables free drive mode. You go back up the call chain, and you eventually realize, based on some other debug output that's been left inside the binary, oh, these bytes, these command bytes, are coming straight over a serial UART from the Bluetooth controller. So if I want to send this free drive command to the scooter controller, I send it via Bluetooth. So this is sounding positive because Bluetooth is local. But now we need to figure out how we reverse engineer the Bluetooth hardware. Thankfully, the Nordic NRF52 is yet another ARM. So this one board contains an incredible number of separate ARM cores. So it's the firmware for the NRF52, which we can also dump over SWD, is split into two large components. The first one is what Nordic call the soft device. It's the actual Bluetooth protocol code. It sits It's given to you in binary form. You choose the appropriate soft device for your hardware, and then you link that into your firmware. Above that, there's your application code that runs on top of that is derived from the Nordic SDK. Nice thing about the SDK is that the source code to that is provided, and if you've got the ability to decompile the firmware back into something that approximates C, you can very quickly line up the binary functions with the SDK functions, figure out what this code is doing, and look for the actual application logic. So got through there and found, OK, there's only a small number of functions in this that are not from the SDK. So that's great. Those are probably the interesting ones. So Bluetooth low energy, basically you expose a bunch of attributes, you connect, you send stuff to those attributes, you write to those characteristics, and then something happens. So in this case, one of the attributes you write to it, and then that gets put onto the serial line and gets passed over to the SoC. So brilliant, straightforward. I just write this command to the correct Bluetooth characteristic, and then the scooter unlocks. Sadly, no. So Bluetooth itself and Bluetooth Low Energy, the connection level stuff is encrypted, reasonably secure, not very secure, fine, whatever. We're talking about stuff that's at the level above that. So I was looking through this, and there's a code path where certain commands will only be passed on if a global variable has been set to 1. And that variable is only set to 1 through a somewhat convoluted code path, which had some big, very complex functions that did a lot of complex mathematics. So look through those. One of those has a pointer to a just table of values, took those numbers, pasted those numbers into Google, and Google said, oh, yeah, that's the AES SBox values. So I now know, oh, it's AES. And so I've now got the encrypt function because it references one set of SBox values. I've got the decrypt function, which references the other set. So now I know where the encryption and decryption are. Now, what made this even easier is that Nordic sell dev boards with the exact same chip as the one that was on this scooter. So I was actually able to flash the scooter Bluetooth firmware onto this dev board, run it directly, and investigate it plugged into USB instead of having to use my chunky cable. So I could just set a breakpoint for the entry to the encryption function, and then, well, I've got my encryption key. But that's not very interesting. So I went further. It's AES 128. We've got 16 bytes of key data. 8 bytes of that are hard-coded values. 4 bytes of it seem to be randomly generated and are then stored in another Bluetooth characteristic. So you can read that value from the scooter and incorporate that into the key. And the final 4 bytes are take the serial number and then pass it through the A2I function. This is an interesting choice because A2I stops parsing at the first non-numeric character, and the serial numbers start with N. Which meant that that bit of the key was basically always 0. Now, to be fair, the first generation scooters actually did have some numbers, not a lot of them, so this wasn't completely ludicrous anyway, not the best choice. So you use that key to encrypt another key. As you can see, the other key is very high entropy. The encrypted key is then your actual encryption key. I don't know. You stick OXB13D, which looks sort of like Bird, and then you encrypt this value with the encrypted key, you pass that, and then the scooter goes, ah, right, you're authenticated, and now you can send the free drive mode thing. And you do that, and the scooter goes beep, and you get on the scooter, and it goes, and then about 2 minutes later, it stops going, because apparently it's still talking to the central network, and it told the network that it was unlocked, and the network was, well, that's strange, you shouldn't be, and sends a lock command, and then the scooter stops going again. Well, okay, fine. I can steal a scooter for 2 minutes. Anyway, so we can go past that. We can check whether the firmware on the scooter is actually validated in any way. Answer, no. Interesting design choice on the Birds. The throttle control and on ones which have electronic brakes, the brake control go through the control box. And so you can, if you want, for instance, just modify the firmware so that after a minute the accelerator stops working and people are, oh gosh, my scooter has mysteriously stopped working. I mean, the alternative would be that you disable the brakes and set the throttle to full, but that would be bad, so don't do that. And then, as we mentioned before, the scooter talks to the internet. The modem runs Linux. You can attach a serial port to it. It speaks 1.8 volt TTL. The root password for the modem is OE Linux 123. I didn't find that out. I just Googled for the modem name and found an Osmocom page that gave me the root password, so that was good. Google makes a lot of things much easier. Sorry, I'm not supposed to be advertising. Anyway, but the fact that the modem runs Linux is entirely unhelpful. Nothing on the application processor on the modem is used here, except for parsing AT commands. The modem speaks SSL, so it can do an encrypted communication back to the server without the STM having to have an IP stack. You can trace the modem access by just running GDB with a breakpoint on the application processor. Every time it sends something to the modem, you break, you dereference the pointer, and then you just pull out the text. So that way you get debug output even though they remove the debug function. And then you figure out that, yes, you can be a SCUSA. You can connect to the SCUSA network. You need to send a SCUSA serial number. This is very straightforward because they all broadcast their serial number over Bluetooth and also over their API. And you need an IMEI. But the fun thing is it doesn't need to be the SCUSA's IMEI. It just needs to be a valid IMEI. At which point you can be a SCUSA, you can update the locations of SCUSAs, and when you connect, the SCUSA loses its connection to the internet, and you are now the SCUSA. So I would like to say thank you to Bird for not suing me.